Hello, everyone. It's really a pleasure to be able to be here and connect with everyone in this community. Okay, so without further ado, let's get started. So I decided to focus on a collaboration of topics that kind of look at a workflow on a more macro level, and it kind of boiled down to the idea of working smarter, faster, and more securely. But before we get into the talk, let me just introduce myself and the PhD project I'm working on to give a bit of context. Okay. So the project I'm working on is called Bayesian Adaptive Design for Sampling on Stream Networks. So I think the most important thing with any project is to start with why. So why are we interested in sampling water quality on river networks? Well, water is a vital resource. And in Australia, 96% of our water consumption comes from river networks, let alone the environments and ecosystems that rely on that. And a lot of the river networks in Queensland run off to downstream environments, like coral reef habitats and so forth. So we want to measure sediment and nutrient concentrations, water temperature, all of these important aspects. We're working with a few industry partners, and I can't go any further without mentioning my supervisors, James, Kerry, Paul and Edgar, the dream team. So what is adaptive design? Adaptive design is an optimization framework. We have a model that we look at why. It's called a response variable. Could be water temperature. We would be interested in water temperature to ensure that fish populations continue to thrive. Above certain thresholds or tipping points of temperature, we will see rapid declines in fish populations. So say we're measuring water quality, water temperature. We know that it's related linearly to air temperature and so forth. So we've constructed this model and we have some data. We may have a little bit, we may have a lot, but within our framework, we can always incorporate more data and have better learnings about what our how the relationships, have more of an idea about how they exist. Then we have some sort of utility. A utility just describes worth of experimental aims. So you might want the best ability to be able to predict water temperature across the entire network. And what it might look like is placing sensors over a wide wide area, but you might be interested in really honing in on the relationships that exists between water temperature and air temperature, having more certainty about the model you're working with. And for that, you might want more clustered sites just to get to back out that what we call a covariate. And lastly, we have a design space that we need to search within. There are a few algorithms that do a big search, but at the end of the day, what we want is some sort of spatial design that says at this location and this location and this location, that's where we should put our monitoring sensors for the best, highest utility or worth. And of course, all of this needs to be coded in R. So that's what I've spent the last year doing. It's not only river networks. I've seen applications of adaptive design in so many places. It's an emerging field, especially the Bayesian component of it. I'll talk to you about Bayesian statistics in the following slide. But so this is an example of ecological monitoring. We don't only have to optimize over where spatially, but also when. So if we add another dimension, time, we can say in the summer months, We want closely related sites in the winter months, not. And even what type of sensor, high cost, high quality, low cost, low quality, and how much of what will give us the best cost benefit analysis. I've seen big data applications. So, and this could relate to any industry that uses big data. So you could design so that you're looking at what data streams to look at, so that you're effectively learning almost 100% of what you could be with far more data. So you're really, increasing your efficiency with limited ability to process data. So you're getting the best possible data streams. Pharmacokinetics, that's how drugs or drugs move within the body. And I've seen a lot of studies with adaptive design. So when to take samples from patients so that they can, with the most certainty, understand concentration levels. I've seen model discrimination work being done. So you have some sort of model and it fits with some degree of error, and then another model, and just finding out how to best model fit in the scenario. Okay, so this is an example. This one here. Oh, that's okay. I might need it later. Okay, so I touched on this model earlier. So here we have a river network, and we have a whole bunch of sites where we have our measured air temperature, slope, drainage, elevation. We call these covariates, and we can construct water temperature using some weighted sum of all of these and an intercept term, say that's theta 5. And so we have our parameters, theta 1, 2, 3, 4, and 5. The Bayesian component of it almost philosophically means that we understand values to be not points, but distributions. So theta 1, I've got an example down in the bottom corner. So say that, so we have these relationships that exist, and we have a better understanding of the distributions of the blue and the gold parameter values. And we're quite unsure about the rest. But in this framework, in this field of statistics, we're better harnessing the randomness, or we call stochasticity, of values that exist in our world. So the Bayesian design framework understands that we have these distributions and we seek to learn more about it. And these distributions become more narrow or more certain the more data that's being incorporated here. So what if we wanted to predict our water temperature value at every value in the river network? Well, the problem that we have to solve is how to get air temperature, slope, drainage, and elevation at these values. And so I'm going to walk through an example today about how we interpolate or find out these values only given the values that we have known quantities for. So there's a method called 3 nearest neighbors, which just looks at the distance between these triangular dots and takes kind of the weighted sum based on the nearest point has the greatest weight, and then we can retrieve some estimates of these values and then continue in finding our response variable. So that gives a bit of an idea about the context. So for the rest of the talk, that's fine. For the rest of the talk, we'll be talking. we'll be going through the R code that's been used. So working smarter, faster, and more securely. So I thought we would start with more securely. Who here, if you could just say in the chat, who here uses RStudio, the RStudio interface? Yes, yes, yep. Okay. Great, okay, that's amazing, so many. Who here is familiar with Git? Oh, okay, wrong screen. Thank you for letting me know. Got it. Okay, all right. Familiar, would like to use it, but don't know how yet. Okay, great. So the plan is I want to show you how to connect Git with the RStudio interface. So it's a matter of, it's just so easy once it's intertwined with with RStudio. It becomes a lot easier to commit and push. And so after that, we'll go on to modularising code with an example of the interpolation. But the interpolation, instead of having a network structure, I thought it would be better to look at just a two-dimensional space. So there's a coral reef shoal that the probability of finding coral is related to the depth of the shoal. So what we can do is for a given number of measurements of depth, we want to be able to interpolate the entire area. And finally, we'll finish with sending jobs to the high performance computer. Okay. Right. All right, so first things first, jump onto GitHub and create a repository. Figure out what your name will be, ideally before you start screen recording. If not, think about it once, think about it twice, take your time, it's okay. Maybe change it if you're not happy with it. For right now, I'm putting on private, and I'm choosing not to include README or gitignore files only because I have some code already that I know I want to connect already. So I've started working on some code and now I want to make a Git repo out of it. So you'll see this screen once it's been set up, and take note of this code here. We'll be needing that later. Okay. That's it. So we've now set up a Git repository on GitHub. The next thing we want to do is go to RStudio. And here we are. We want to create a project of an existing directory. I've got Clearwater directory, or I put all my code and I want it to become a project in RStudio. Okay, I was thinking about it, and then we have that, and on the right-hand panel, you can see all of the files that are in the project and a .r project file, which stores all the R data so it doesn't contaminate any other R projects that you have. So then we go into Git, version control. Okay, and look to the right-hand panel at the top. We should be able to see Git come up there shortly. There we go. Okay. So we see Git and all of the files that are what we call, well, there's changes made. They're all new according to Git. There's Git ignore. So there's files down the bottom I don't want to see. I don't want my results to be committed. So I'm going to specify that the results folder isn't, just ignore that basically. And I'm going to do the same with scripts. There might be things that are just too large that you don't want in there, or that you want to keep private still. So I'm going to commit, my first commit would be the Git ignore file. And so this is what it'll look like. Just tick the box and then you see the screen A and commit it here. Write a message. Okay, when you've seen this, it's worked successfully and you're all good to close it. You can still do all of this from the command line too without these buttons. But I mean, it's just really easy. Okay, so right now we've committed it locally. Oh, so you can't see the results and scripts. I think that was the point of the committing the Git ignore first. Now we're going to commit the rest. It's a little laggy because there are a lot of files here. They're all highlighted. Did that stop already? No, it's just here next time. Okay, there we go. Sped it up a bit. So we're committing these files too. Okay. Sorry, it's going extremely slow at this stage. It shouldn't be. There. Okay, so we've committed everything now and it's time to push. So this is where the code we saw before, where we've committed it locally and we need to do our first push to the branch. So go to the terminal and we only need to do this once. You're connecting the local to the remote. We git branch the main, establish the main branch, and then we push. So this recording will be available on YouTube if you would like to come back and retrace these footsteps. But once this is done, it's done, and it's just a matter of clicking commit and push further down the line. So some sign-ins. I'll show you then what it looks like. So we needed to sign in to authenticate just once, git push, and it's done. Hooray. So at this stage, we're just making a change, and we can see what that looks like by committing and pushing. All the files. Here's our change. And we push to set the change. At the very end. There we go, making a change. It comes up in our Git repository. So yeah, let's get on to coding. How is everyone? I'll check on the chat. Okay, cool. Thank you, thank you. I see some questions are being answered there. And yes, the slides will be available after the talk. Okay, all right. So we have now switching, okay, great. Switching gears a little. So we have a problem where we have, we want to understand what the depth of a shoal will look like in the ocean bed, and we can only take measurements at certain points. So the first thing we need to do is kind of synthesize some sort of depth space. So what I'm going to do now is create a function to do that. So the first things first, let's start with establishing a grid. So if we have a grid space, say X ranges from 0 to 10 and Y does 2, and we're going to establish a sequence from 0 to 10 of length 10. That's great. But before I go any further, I'll just, so what I really wanted to focus on here was how a project should best be structured. So we have some main file and then some worker functions within this R folder. And so we're looking at, there's two jobs basically: to generate data, to take samples, and to interpolate that. All of this is controlled in the main script. And then we have what we call shell scripts.sh to ultimately run that later. But I want to break down the lines of the code before we do that. So we can look at our functions here. We have this domain from 0 to 10, and we have some sort of granularity on what what this domain would look like. Do we want 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, or do we want 100 steps between that? So we just run the grid and get a grid. So we look at this function here in generate data. So we've called the function source has said run this generate data file, which introduces functions. So we can then use that and we can get the grid. So we have x1 and x2. I'll make this smaller. So we only want 10 sample points within it, so that our x1 and x2 looks like this. Okay. Now we have a function called getDepth. Okay, so here is where we've constructed a surface given x1 and x2. So the first thing we do, we have points, say we have points 1, 1. A 10 by 10 grid equals 100 points. So expand grid creates all of these 100 points by fixing y and saying iterate through x1, x2, x3, x4, x5. The next y value 1, 2, 3, 4, 5. So we have 100 points in a 100 by 2 column. And so what this function does is basically utilizing density functions just to create some what we're calling synthesized depth. So let's have a look at what that looks like here, and we can plot it. It's not very smooth because we have a 10 by 10 grid. If it were to be 100 by 100, 10,000 points, we can picture what that looks like and perhaps a better idea of really the smooth nature of it. But I always like to minimize the dimensionality when I'm just kind of testing and what we're doing here. So back to 10 by 10, this granular kind of looking now. Okay, all right, we have this. And so all the possible points that are there, let's contour it, of course. All the possible points that are there look like this. Okay, so we have 100 possible points in this domain. We call this discretizing a domain, a continuous domain, which makes sampling a little bit more reasonable. Okay, so what we've done is we've expanded the grid and combined it with depth. So how do we get depth? We have this 100 by 1 vector and we've c-bind it. So then we have data that looks like that. So we have a depth corresponding to each coordinate point like this. Right now there are 100 of them. So then we're going to sample from this space. So we've got sample from 1 to 100, 1 to 100, back to 10. So the number of grid squared, that's how long our data is. And sample our second input variable, sample 100. In this example, let's make it 10 because there are only 100 options. Sampling 100 from 100 options gives us everything. So let's see, in the reality of it, we would only have depth for the amount of sites we can measure. And we're synthesizing an example where, we're trying to find out what all of the other sites will be. So okay, so we have 10 sites that give us 10 sites here. So we suppose that although we know what this domain looks like. We've only actually figured out the depth at those 10 places. So then what? How are we going to interpolate to find the rest? So we construct the distance between these 10 points and all possible 100 points, and raster points distance is a great way to do it. So we have data, and we have our sample index. This is the index of our 10 sites. And so we've just selected the rows from data using this sample index and taken the first two columns, which are the X and Y, or in this case, X1, X2, however you want to name them, X and Y values. And so we have our coordinates as sample X1, X2. So we find the distance here between two, in this case, 2 by 100 as an expanded grid and 2 by 10 matrix, which gives us a distance matrix. Helps if you run code before asking what the values are. Find me the dimensions. So as expected, it's 10 by 1. Look at what that looks like. Okay, so it's saying between 0.1, i.e. the first row of all X1, X2 points, and the first X1, X2 of the sampled points, the distance between that is 8.67 units, and so on. Okay, so we have this distance matrix. So now we can interpolate the depth. That's really all we needed between all of these points. To do that, we've created a function called interpolate depth. So we know that on this matrix, every row represents a value that we don't really know yet, but we want to know. And we know the distance between the known 10 values. So we take it row by row and figure out what the depth value is. So I kind of like to break down functions with naming the input variable for now. Let's just pretend we're working with the first row before we apply it to all the rows. So as expected, the distance is that top row. Okay, so let's, it's just a matrix and we can't select it by indexing it. So we're just going to name the distance matrix row. Looks like this now. And we're going to find the nearest neighbors. So we sort this vector on the values. So the closest is 2.11 is 2.48 units away, and that's at the known 0.7 and then 5 and then 3. So we take these neighbors and we call them nearest neighbors. If the distance of the first nearest neighbor is itself, i.e. you found the original point, then just return that point. Otherwise, sample from the depth. We have 10 values here, sample the nearest neighbors, which we found to be 7, 5, and 3. So we construct a weight for these 7, 5, and 3. They can't be equally weighted, given that they're all different distances apart. So we use the inverse of the distance. That means the closest distance has the highest weight. So 1 over distance of the nearest neighbors, which makes sense, given the nearest neighbors' distances are this. So the most weight on the first and so on and so forth. So that's it. And then we return our values. I just run all of that properly. Okay, and then we have our depth value. Great, so now we know what's going on here. We call this function, we apply it to each row of the distances matrix. So we have this, and let's see how it did in interpolating all of the values. Okay, pretty shocking. All right, that's to be expected. This was planned, don't worry, fear not. Okay, so it can be improved. Well, now that we know what's going on, we can have a bigger grid. So let's get a better idea of what's going on here. So we have a 100 by 100, a granularity, the original space, so more granular discretized space. So let's have a look at, even with 10 points, let's see how that fares. Okay, shocking. But if we make it 100 sample points and try to interpolate the values, maybe we start to get a better idea. Okay, it's looking a little better. 10,000 sample points. And you can probably see if we, yeah, you can see how closely now that resembles by using our interpolation of 3 nearest neighbors, given more data to begin with. Okay, so we've spoken about modularising code, having a main function that does the body of work. This is good, but it could get a lot better. So firstly, we can define this elsewhere. If we were to define this in what we call a shell script and let a high performance computer do all of this work for us, it's a good workflow to establish what I wanted to show you today. So we don't need all of this plotting if we just let the HPC do the work for us. So if we're just going to tidy this up to really just have the interpolation and saving our entire image to a folder called results, and then we'll just have a .r data which saves the global environment, and you don't have to worry about specifying what objects you want. So everything's there. I found that's quite useful to debug later on, because nothing ever works the first go. So the other thing was we had a seed value. Often, particularly in Bayesian statistics, it involves a lot of reruns and setting different seeds and a lot of data generation. So I included it because it's a typical thing you'd start to see. Okay, so we have main. So now what? Well, we want to send this file as it is to the HPC. So how do we do that? Well, we have a few different ways. Let me just show you what the folder looks like. So if there were any pre-processing, I'd probably run that and put the data in there. In this example, it's empty. We generated that on the fly. We now have our results that are populated because we ran that code once locally. But now we can have a look at how we would send this this instruction to HPC. So let's have a look at run example 1. Okay, so here we're giving instructions on the configuration of nodes and CPU type, wall time, memory, and we're naming the job. We're naming it example 1. Then the variables we saw at the beginning of the R script we've put in here. And we're saying, okay, change directory to where this shell script is, load. Well, you'll need to load an R module. And this very much depends on what modules are set up and available. But ask for help at the HPC. I'm just flagging that at QUT, these are the modules that are set up for us, but they very well may differ for other high performance computers. And so we run our main script by using the command rscript main and then our arguments. Okay, the only caveat with using this is that you need a piece of code in the first rscript that says command line args, collect them. I didn't want to include that so much because I moved straight on to example number 2. So here is an alternative to this. I've seen people do it both ways. I wanted to show a variety of options. Example 2. So this gives the same result at the end of the day. So we again established our instructions for our job. This time we're also saying for the .i and .e files, send them to a subfolder when naming script. Okay, again, we change directory, we load the modules, but here we're opening R and executing this code. So we're naming our variables ngrid, nsamples, seed, and then source like we did before in R. So we're doing that this way. So there's a third example here. If we wanted to run a whole bunch of these with multiple seeds, multiple samples, different grid sizes, we can build on this and say, okay, all right, so I want to run it for 10 seeds. So again, we establish our initial variables and then we say for, this is in bash, for seed from 1 to 10. So keep looping through. Create text files and create a shell script that looks like this. So write the name, the CPUs, memory, scripts, load the modules, change directory, and run. Note that we have variables here that are established up here, and run it and end a file, and then queue sub, and then submit this shell script once it's been written by this master shell script. Okay, so if I were, I'll show you. So once this is run, you'll get these 10 shell scripts, which look like this. And you can see it's exactly the same as example 2. We've just used another shell script to bulk run them all at once. And the final way to run this is to open up an interactive terminal. Yeah. So SSH to the HPC. It just means log on. Here we are. So what we would do in any case, so here I'll just construct into these. That's there. So in example 2, the command you would use is qsub. In example 2. Qsub. The command to run the example 3, the shell script that generates a whole bunch of other shell scripts, is ::, and then that shell script that will in turn submit or qsub all of these individual shell scripts. I'm just checking the chat now. Okay, I might stop it there. And open it up to, I'm reading the chat as we are, but I hope you enjoyed the quick kind of overview of modularizing code, sending it to the HPC, and a little bit on Bayesian design. Thanks. If anyone has any questions that they would like to say.
I guess there's a question from Jade, just the HPC's new, when would you recommend doing something?
Okay, when would you recommend doing something like this? Overrunning in RStudio. When it gets to a point in RStudio that you're waiting way too long. Yeah, the only reason
a lot of the time, so maybe I can use something like this. I'm waiting and waiting every day. So yeah, thank you. That's a good recommendation.
And running things in parallel. So if you have this one, in my case, to compute a utility takes a really, really long time. So, but I want to do that for hundreds of different designs. So I send those 100 out at the same time, and they each take hours. So in the space of 3 hours, with maybe 10 times the power of what would normally be done in RStudio, it's just a 10-fold times 100-fold.
And just quickly as well, if this is something I want to do you know many online resources that I can use to sort of guide me through that process while I'm doing it as well? I feel like I'll get stuck.
That is an excellent question, and it's so easy to get stuck. Not saying that to discourage, but I've just been there before, and I know. May I ask what uni you're from? I have some QUT specific help with our infrastructure and some general help as well.
I'm actually based in Thailand, so completely different.
Okay. Oh, that's so cool. Cool. I will send both to.
Do you want to? Is it like a general resource? Like
general resource.
Do you want to just type them in the chat maybe, and then?
Oh, I don't know them off the top of my head.
Oh, you don't know? Okay, that's fine. Yeah, we can send them out.
I'll have to go digging through the inbox, which I'm sure is not something people want to see right now. Okay, yeah, we'll post them on the GitHub. So I'm new to modularizing. So you divide the code. Yes, I'm sorry, I do not think I did a good job explaining this. There are packages that we're all familiar with in R, and they're the library import kind of packages that we install. A step back from that is arranging code into files, each that perform a siloed kind of function or task.
Yeah, that's cool. It's probably organized better than having loads of things in one project.
Yes.
Cool. Thank you.
Welcome. If you are, good point, Paula. If you are the UQ contact, if you are at UQ, contact the RCC Research Computing Centre and visit Happy Hour.
QUT has Happy Hour too, right? Probably similar resources.
I'm not sure, but I know that there's a HPC centre for those at QUT that you just need to get a login and find out some information like what modules are there and whatever else you need. In terms of packages, Are there limitations with running R on the HPC? Yes. Or am I missing something here? What if a package is not installed on the HPC? I was almost going to run through an example of how to install a package. So you need to install all packages that you use in your library. I've seen people specify library paths, but I've come into problems with that. So I open up R, so I module load. So yeah, I can go through that. Basically, the command would be go on to the PuTTY that I had before, bin bash. I can send you this code to module load, open R, and then as you would install.packages, and then you'll be asked what CRAN mirror, and then it's the same kind of process, but on the HPC itself in an interactive terminal. That was a really good question. Okay. Our latest did a whole session on Git and Rstudio, which is on GitHub. Yeah, great. Is a shell script a file, just a text file? Yes, basically with the script to run the job. Yes. Yes. Shell is a script for the Bash language. And it serves as a control center for running for creating instructions and running scripts.
Is there any resource on how you serve Bash for like sending stuff to HPC?
That would be in. Okay, we have a question here. Are there any resources for other for Bash scripts sending jobs to the HPC? Actually, I'm not too sure, and I think that's part of the reason what motivated me to talk about it today. I hope this will serve as a resource. So the code that I have been talking with you today will all be on GitHub, and so those Bash files, scripts are there for you to see and access anytime in the future, and for you to make necessary changes to any configuration that you want. Thank you. Thanks, Evie. Thank you. Thanks, everyone, for joining us. I'm super stoked to be a part of this and super stoked with the turnout. Please, if there were any questions I missed, feel free to write them. I kind of might have missed one or two. Thank you.
Yeah, I guess with that, if we can, I guess there's one last question. Sorry.
Okay, is there a way to run an Rstudio hosted on a HP3 through a browser? Oof. Yeah, good. Oh, look, good question. I'm not sure. To run an Rstudio hosted on the HP3 through a browser. Okay, so what, I think this might be answering your question. So I mapped a directory to the HPC and I set a working directory as the Z drive, which is the HPC. I can show you. So I effectively work directly on that, on the HPC through R. It's a different project of mine. But I can open that up and show you. Clearwater. Here is my mapped directory, HPC, and I have R files. I just don't have RStudio. That's right. Thank you. Okay, here we have Windows, U Drive, and this is my map directory. There's .r files, so I can really easily go in and edit them. I just don't have, I mean, that'll open in RStudio or whatever text editor you prefer.
Is Pate QUT specific?
Pardon?
Is Pate like QUT
Pate.
specific?
No, PuTTY isn't QUT specific. Yeah, PuTTY is a general ability, SSH kind of log into a Linux box. I'm on a Windows machine. Thanks, Katie and our ladies. Always great to see other people's workflows. Yes, I hope you all took something from that.
Yeah, well, I guess if no one has any other questions, if we can all just officially thank Katie for her great presentation. Thanks.